Okay, well, thank you very much. First of all, I'd like to thank the organizers to restarting the Back to Swamp workshop series. It's very exciting to speak here, and thanks for the invitation. As I mentioned, as Anna Maria mentioned, I will be talking about tameness of quantum field theories and control field theories. And it's based on a paper, an upcoming paper with Mike Douglas and a postdoc in Utrecht, Lorenz Schlechter. And well, I didn't fix this yet. So this number here, this goes up with every month by one, but I hope at least by the end of the next month, we will be done, hopefully. Okay, so what will this talk be about? Let me give some swamplandish motivation. Namely, last year I thought about if tameness could be a general property of the landscape of effective theories compatible with quantum gravity, and I put this into the notion of a tameness conjecture. And this talk will not be about this tameness conjecture in particular, but this talk will be having an eye on maybe tameness is actually a very general feature of a theory of quantum gravity itself. And we slowly want to work into this direction, and we want to study various theories where we can actually test these ideas. But if you see this slide, you might ask, and if you see the talk of the title of my talk, you might ask, so what is tameness? So if you never have heard about this before, then I need to give you some of the details. Tameness is a generalized finiteness principle, and one way of thinking about this is kind of a finiteness of structure. So if you have a function that it can have only finitely much non-trivial structure. What does it do? It restricts sets and functions into tame sets and tame functions. Okay. So let me explain what is not allowed, and then I will tell you a little bit how this is built up. So first of all, it avoids wild functions and sets. So in particular, infinite sets with disconnected components with kind of like the integers is not a tame set if I take all the integers, or any lattice is not a tame set. Okay, and complicated functions are also not tame functions. They can never be tame functions. For example, the sine curve, the topologist sine curve, which is kind of accumulating infinitely many zeros around this accumulation point here, is not a tame function. So that's the sort of thing we want to exclude. So there is some general finiteness in this. But where does it come from? It actually comes originally from first order logic. So actually these structures, these tame structures were introduced by logicians. And they, in logic, kind of finiteness is something nice to have because you want to say that something is true and something else is true. And then you want to kind of compose statements, but only out of finitely many things being at the same time true. And in particular, one of the motivations you might want to put on this is kind of you want to avoid some logical inconsistencies like these undecidability properties, which you get over the set of integers. If you make a logical system over the integers with arithmetics, then you get undecidable statements, fundamentally undecidable statements. Another perspective on this is a more geometric one. In fact, Grothendieck put forward this idea of having a tame topology, which is a topology which is used for geometry. In some sense, you can think about it like this. If you think that all of physics is somehow at the end of the day geometric, then it should be describable within this tame language, so in this tame topology. Now, let me be a bit more concrete. First of all, if you want to learn about this subject, there is a very nice short book by Van den Dries. It's easy to read because it's so basic, right? It really starts with the most basic thing you can imagine, namely defining what are the sets of the system. If you enjoyed this and then you say, oh, I want to learn more about this, there was a 6-month program this year at the Fields Institute. There are, I don't know, maybe 100 or 200 talks online. So you can spend many sleepless nights watching this. Okay. So I should explain a little bit what an ominimal structure is. So an ominimal structure is the structure which generates a tame geometry. So what is this? It's a collection of subsets of Rn for every n, which has some nice properties. Namely, it is closed under finite unions, intersection, complements, and products. So every sort of finite operation you can do with a set, which we all know, all the set operations, is actually preserved or is allowed in this collection of sets. Very importantly, it's closed under projections. So if I take a higher dimensional set and I project it down one dimension linearly, I find again one of these tame sets, or one of these sets in the structure. Yeah. Now, in order to make this a little bit more interesting, we already include all the sets that are defined by polynomials. So take a polynomial equation, x squared equal to 0. Well, this is very boring, but with multiple variables, and take this set, and this set will be part of any of such structures. Okay. All the polynomials are there, and these are called the algebraic sets. Now, what is now a tame structure, so an ominimal structure? Well, it's a very simple condition, and that's somewhat surprising, and only when mathematicians realized that this simple condition produces so much interesting mathematics, kind of the field really developed. That was in the end of the 90s, or middle of the 90s. So what is this tameness condition? It's very simple, namely the statement that if you look at the real line, that the only tame sets on the real lines are just finitely many points or intervals. So I give you some examples. So any collection of finitely many points or intervals is a tame set. Okay, these intervals can also be infinitely long, but you see that the integers would be infinitely many points, and they are not a tame set, right? Well, okay, and how does this propagate to the higher dimensions? Well, because of this projection property. Now I give you a higher dimensional set, which is very complicated, but you have to make sure that whenever you project it down to 1 dimensions, it has to only reduce to finitely many points and finitely many intervals. So what are now the sets in an ominimal structure? Well, these are the sets which are in S and have this tameness properties, and I will call them tame sets. Okay, and the functions are tame. The function is tame if the graph of the function is a tame set. Okay. And having this, you can now define a whole tame geometry. You can define tame manifolds, tame bundles, and so on. And you have to keep in mind, whatever you can draw on a piece of paper, that's typically a tame thing because it's very geometric. You cannot draw infinitely many points on a paper, and that's exactly the issue. So to say. Okay, very good. Now, how did I get into the story? Well, we proved the theorem, namely we proved the theorem that if we look at the type 2b flux landscape and we look at G4 fluxes on the Calabi-Yau fourfold with these conditions, then the vacuum landscape of satisfying all these conditions is actually a tame set. So what does that mean in particular? There are only finitely many fluxes and finitely many vacuum loci. Okay, so that was something open for 20 years, and in fact, it was only due to these kind of advances in tame, in this tame geometry that this proof was possible. It's very non-trivial to show this. Okay? So it's by no means obvious. Okay, and then another kind of motivation of this idea that tameness is there in string theory or string theory effective action, that if you look at the effective action, that all the appearing functions appear to be tame functions of the moduli. There are also an interesting relation between tameness, the distance conjecture, and the axionic string conjecture, which we pointed out recently. But what do I want to talk about in this talk? I want to actually now discuss quantum field theory and conformal field theories and ask if tameness is somehow manifest in this. So are quantum field theories tame at the perturbative level? Well, the answer turns out to be yes, if they are renormalizable. And this turns out we can actually prove this. I will show you that we can prove that all Feynman integrals always lead to tame functions. Now, if it is a non-normalizable theory, we don't know if the functions are tame or not. In fact, in this case, it will depend on the UV of the theory. So how do you actually deal with the non-normalization issues, right? How you cancel the divergence. Now, are QFTs at the non-perturbative level tame? The answer is, in simple examples, yes. Okay, so I will show you a few examples where you explicitly see that the partition function computed non-perturbatively is actually a tame function. In general, again, it depends on the UV structure. So it really fits into this picture that eventually this has something to do with the UV completion of the theory. The next question is, are CFTs tame? Is the space of all CFTs tame? And the answer is, we think so. Yeah, we actually have strong belief because there the UV somehow is in the story, right? Because the CFTs don't have a scale. Okay? And since I have a theorem, I'm allowed by a new rule which I made up to put a conjecture. So whenever you have a theorem, or whenever you put a conjecture, you have to prove a theorem, which is true in my case. And so my conjecture will actually be that all correlation functions are tame functions. So whenever I give you a CFT, you can check all the correlation functions, and you should find that they are tame functions. In fact, something even stronger is true, that the set of all CFTs is tame if we put some bounds on the degree of freedom. Yeah. And I will explain this in some detail. So now let's come to the first part, tameness in perturbative quantum field theories. What is the theorem what we want to prove? We want to show that for any renormalizable quantum field theory with finitely many particles and interactions, all finite loop amplitudes are tame functions of the masses, external momenta, and coupling constant. So that's a statement. It's a very concrete statement. Everything is well defined. So what does it mean? It means if you draw a kind of a Feynman diagram like this, and you want to compute the amplitudes to it, then it will depend on the masses of the particles which run in the loop. It will depend on the coupling constant, and it will depend on the external momenta. And the statement is that this function, in the sense of which I described before, is actually a tame function. So it can never have wild behaviors, even in its singular limits. Yeah, so in any dimensions. So there is some sort of hidden finiteness property in all QFT amplitudes. And it's not a finiteness property that there are no divergences or something like that, but it's much more subtle than this. Let me put a few remarks. The theorem is very non-trivial, and you will see this in the proof. And it has interesting implications for Feynman amplitudes. So this is, we will not put this into the paper, but that's something which we are thinking about a lot, because that's exactly what mathematicians do. They combine tameness with say, analyticity, and then they are able to show very non-trivial relations which you would have not expected otherwise. And we can do that also for Feynman amplitudes now. An interesting thing to point out is that tameness is already useful without gravity, right? So it's kind of in the swampland perspective. It means that there is kind of a remnant in the well-defined theories which we have. Any renormalizable theory is already very well behaved under this kind of tameness conjecture that everything is tame. So this is nice, and it's even useful for something. So how does the proof go? Well, it relies on facts about amplitudes, and one very important relation, namely, first of all, amplitudes can always compose into finitely many Feynman integrals. Yeah, finiteness is very important in this. And then the idea is that you represent the Feynman integrals as integrals on auxiliary manifolds. So you introduce a manifold, a higher dimensional geometry. It's not like the string compactification space, but you just make it up such that your Feynman integral is actually a period integral, so an integral over some cycle in this manifold. Okay. And then you can map the parameters, so the masses and the couplings and so on, and the external momenta. You can map it to the moduli space of this geometry. Okay. And then kind of your Feynman integral becomes an integral over a cycle in this geometry. And the important point is that all steps in this construction involve only tame maps. So in this identification, and then you have to use a very non-trivial theorem, namely that period integrals are tame maps in an Ominimal structure, which was only shown this year in this work. Now, what is the key point? If the theory is renormalizable, we have only finitely many counter terms. And these counter terms are, again, formed from kind of interactions and so on. And we can apply the same logic, and we can make the theory, and it makes the theory renormalizable in a finite way. And the whole thing is, again, tame. So in the non-renormalizable case, where you have to add infinitely many counter terms, like when you want to renormalize quantize gravity, for example, you lose this immediately, the tameness. Okay. Now that's very encouraging. So it's a property of renormalizable quantum field theories at a perturbative level. So we were very excited about this and thinking, well, maybe then every QFT is also tame at the non-perturbative level. And the way how to proceed on this is you first check some examples. Well, there's the Sine-Gordon model here in 0 dimensions, admittedly very simple quantum field theory. And what you find is you find some Bessel function. And in fact, this modified Bessel function is actually tame. Why is it tame? You can again construct a geometry where this is exactly the period of this geometry. So we're very, very happy about this. Then you can do quantum mechanics. So we look at the harmonic oscillator, and you find that this is a Sinch function. And Sinch is actually made out of exponentials, and exponentials can be turned into tame functions or are tame functions. Okay. You can look at free Young-Mills theory in 2 dimensions. Now theta functions appear. Theta functions themselves are not tame functions. Why? Because they have infinitely many images in there. So if you have an infinite symmetry, that's a problem. Okay. But on the fundamental domain, namely where you use this here, it is a tame function. So also the partition function of SU2 or SUN Young-Mills theory in 2 dimensions is a tame function. You can also look at 2,2 theories, GLSMs in Calabi-Yau compactification, and by their relation to periods, you again find that the partition function, this time evaluated on S2, on some compact space, is actually a tame function. Now, that sounds all very nice, but there's one example where we are struggling. So now there is you can go to 0 dimension. This is a theory which we like, phi to the 4 theory. You can compute the partition function is again a modified Bessel function, and we don't know if it is tame. Well, this is very embarrassing, actually, because it's a very fundamental theory that you expect it to be tame. And actually, it looks completely fine. But here we have to rely on mathematicians to make progress. So even so this field is very widely developed, such questions are not yet answered. So we have a physical problem which we can give to mathematicians and say, this is very important to understand that if we believe in tameness in physics. Yeah. And these are would be called exponential periods, and it's very helpful to show their tameness. In fact, we can ask the more general question, what are the precise conditions on Lagrangians in 0 and 1 dimension such that the partition function is tame? So I invite all of you to think about this. It's a very concrete question, and it's a non-trivial question, but it should have an answer. So what do I have to do in my partition function? What conditions on the Lagrangian I have to impose that I get a tame answer? So there are challenges for tameness. Tameness is, in fact, constraining. So in fact, if you have a global symmetry of infinite order, this is never a tame function. So if you have really a global symmetry of the full partition function, this is never a tame function. This fits very nicely because it says that tameness actually requires that such symmetries need to be gauged or eventually broken in the full partition function. So this fits again with this UV idea that there should be conjectures kind of constraining what is allowed, and in particular, no global symmetries should be allowed. But you can easily make up non-tame Lagrangians. It's not difficult. Put a potential of this form, cosine theta and cosine alpha theta. And this was considered in some string theory literature, but if such a thing would actually come out of string theory, then you have clearly a tame function, a non-tame function which comes out of string theory. But I don't know of any realization where this actually happens. And what happens, for example, the torus, you kind of get space-time filling curves, right? Or kind of torus filling curves. You reach every point on a torus. That's very wild. More fancy is this example by Tachikawa put forward. So there's also a non-tame piece here. And he puts this forward in order to get non-decidable questions in a quantum field theory, namely whether or not it has supersymmetric vacuum is fundamentally non-decidable. And the actual reason behind this is because you have this non-tame function. And when you minimize it, you go to the integers. And these undecidable questions are over the integers. So all of these things are not tame, and they should be forbidden by the UV condition. We also think about the RG flow. I just flashed this briefly. You can ask, is the RG flow actually tame? So starting with a tame theory, does it remain tame if you go through the RG flow? And surprisingly, mathematicians studied a very similar question. Namely, they look at such differential equations and ask, when are their solutions tame? And excitingly, you find that there are conditions which you have to impose in order to not end up with what is called limit cycles. So you have an RG flow, which then turns into a cycle in the coupling space. So this is something very wild and would violate tameness. So in fact, we expect that this doesn't happen. And it would be very nice to check if indeed all the physical theories, say in the landscape, do not have these these kind of limit cycles. And it's directly related to this tameness idea. The good thing is integrating out fields preserves tameness. So if you start with a tame potential and you integrate out heavy fields because of these axioms that you can project and so on, you get indeed a tame lower dimension. Now let me come to the tameness of CFTs. I already sketched, so I can be brief on this. CFTs are axiomatically well defined. We can write down their partition functions and their correlation functions, and they depend on points on some manifold and maybe on the points on the conformal manifolds and some parameters specifying the theory. And we can now ask, are these functions tame functions on these spaces? Why is that interesting? It would imply some of previous conjectures, namely about the finiteness of CFTs, if you put certain bound. And in fact, it also would imply that CFTs have non-zero radius of convergence in the perturbation theory, in contrast to general QFTs. So what is the conjecture which we put forward? Essentially, it's very simple to state it, because it's essentially the statement that all of these things are actually tame under certain conditions. So the parameter space is the most tricky one. So because it essentially says that there are only finitely many CFTs, and there you have to upper bound the degrees of freedom. So say the central charge in 2 dimensions. Yeah, in 4 dimensions, you have to maybe put 8, bound 8. If you do that, and in 2 dimensions, you have to also put the lowest operator dimensions have to be bounded from below. It has to be a gap, a finite gap, a fixed finite gap. And if you count all the CFTs which are in this range, it should be a tame space. So in particular, if the CFT are just points, then they are just finitely many. We claim that all the conformal manifolds are tame manifolds, and we say that all the partition functions and any correlation function on a fixed background in a CFT is a tame function of the parameters and so on. More subtle is that we include the idea that the correlation function is a tame function as a function of the position in space-time. Okay, and this is kind of an interesting idea, but it requires that you have to put it on a sufficiently nice manifold. So if your manifold is truly wild, then you cannot expect the correlation function to be tame. Okay, we call this Ominimal structure RCFTD, and in fact, you can try to construct it. So there is a straightforward way, algorithmic way, if you want to construct it, but it's very hard in practice. So you start with the polynomials, and then you add all the correlation functions to construct your tame sets. Okay. And then the tameness question is, if you use this structure generated out of all the correlation functions, is this structure Ominimal? Is this a tame structure, yes or no? And the conjecture says it's always a tame structure if I impose these conditions. So it's a very concrete thing to check for all the examples which we have. Note that this is a non-trivial thing. And in fact, the research on Ominimal structures proceeds now, right? Just this year, a new Ominimal structure was constructed in which the the gamma function and the zeta function is definable. This is tame. So it's really something touching directly into current mathematics. And in the last half a minute, let me ask, so how much do we now know about the tameness of quantum gravity? Well, the first exciting thing to realize is that perturbative string theory is not tame. Why is perturbative string theory not tame? Because perturbative amplitudes have infinitely many poles. So that's completely against the idea of tameness. Like this whole tower of string states is completely against the idea of tameness. Okay, now you say, oh, that's really bad. Now I'm saying that string theory doesn't work. Well, no, maybe in non-perturbative string theory, we are much better off. And in fact, we check this in 2 dimensions. In 2-dimensional non-critical string theory, we can see that the partition function is not tame. But if we go to 3-dimensional non-critical M theory, of course, this is much simpler than in 10 versus 11, but we see the partition function is tame. So in fact, the non-perturbative completion in this case kind of removes the non-tameness. So it's an interesting question if tameness requires the string to become a membrane. right? And we know that in string has discrete states, while a membrane has kind of a continuous spectrum. So that goes exactly in the idea of discrete things are bad and continuous things, if they are just finite, then they are fine. Maybe the best chance we have at getting at the tameness of quantum gravity would be the ADS-CFT correspondence. In fact, from our conjecture, we actually have already a proposal. What is the Ominimal structure which corresponds to quantum gravity in ADS space? Well, it's this Ominimal structure which I construct from the CFT. And everything in this quantum gravity theory should be formulatable in this Ominimal structure. So what does that mean? My last slide. Well, the idea would be to think about the kind of the landscape in the following way. You have QFTs, all of them define what is called a structure. It's something you can construct, but only the ones which are compatible with quantum gravity, which is tame itself, are in the landscape. Thank you very much.
Thanks for questions. Irene?
Hi, Thomas. Thank you very much for the super nice talk. Yeah, I'm wondering, so for instance, sometimes the Swampland constraints, you cannot use them to determine whether a given theory is in the landscape or Swampland unless you give the cutoff, so that it's a correlation between some EFT quantity and the cutoff in which the theory has to change. Can you imagine how to maybe introduce this notion of the energy scale at which maybe some function is not tame in the IR, but must become tame at a certain energy scale because otherwise it's not consistent somehow?
Yeah, so it's a little bit in what I presented in the RG flow story.
Yeah.
So indeed, that's you're absolutely right. So that's a little bit the tricky part of the story, because I don't have a big, or we don't have a clear formulation yet how to use the cutoff in the best possible way. So now we use the cutoff by saying something like, if I fix the cutoff, then things below the cutoff are tame. But if the theories are non-renormalizable, I don't even know precisely how to formulate this properly. So that's what makes it tricky. But my expectation is that it can be done, and you're asking a very good question. I cannot give you a good answer. Yeah,
Okay,
but I think it can be done. Probably the idea would be that the theory has to be a tame function of the cutoff. So it's really in this. So the cutoff should be a parameter. Exactly. Yeah, you have to think of everything as functions again, and these functions are on the energy space. And as long as things are tame on this energy space, then the full theory is tame again.
Hi, thanks for a very nice talk. I think I'm just confused about something. So you were, when you were making segments in perturbation theory, you were working always at a finite order in perturbation theory,
yes.
Right? But then you made a big distinction between renormalizable and non-renormalizable theories. But for a non-renormalizable theory, at finite order in perturbation theory, you only ever need a finite number of counterterms. So why is there a difference? The infinite number of counterterms is relevant if you want to make a prediction to arbitrary accuracy, which you cannot. But if you go to like 2 million loops and you stop there,
right,
you will only need a finite number of counterterms. So is there?
I understand, but usually, if you have a non-renormalizable theory, you have to be careful with kind of your cutoff dependence, right? You have to say, it's not so. At least it's not so clear to me. Maybe you have a better understanding on this. I'm totally open for this. That in this case, there is a clean notion of independence of renormalization scheme, for example. I know there are prescriptions of doing it, but it's not as a clean story as we have for the renormalizable theory.
I think most effective field theories would say that if you're working at a finite ordering perturbation theory, then there's no difference between, like, for perturbative, normalizable, and non-normalizable.
No, I fully agree. So I don't have a doubt that it works also for the non-normalizable theories if you do this carefully. It's just, it's not at the theorem level, so to say. I would
maybe you can discuss.
That would be very interesting. Yeah. No, but the non-trivial part is the summing up the infinite series. So a sum of infinitely many tame function is not a tame function necessarily.
Okay, maybe we can continue.
Maybe we can discuss.
Thank you very much for the talk.